So the main idea in part 2 will be the so-called Kolmogorov's chaining. Before we state that result, let's start with a couple of definitions. So first, let's consider a metric space F with a metric D, which is a totally bounded metric space. Okay, then we'll need the following definition, or two definitions. In the first definition, given a positive parameter u, we define the following quantity called the u packing number, which is denoted by d fd u. Okay, and this is just the maximum cardinality of a set that you can pack inside of your set or your metric space F, so that all points are at a distance at least u from each other. Okay, so it's a maximum cardinality among all subsets of our space F, such that the distance between any 2 points is strictly greater than u, okay, for all f and g in this subset fu. And because our metric space is totally bounded, this will be a finite number. And then a closely related definition is that of a covering number. And given positive u, a u covering number, which is denoted by n fdu, this will be the smallest cardinality among all subsets in F, such that for any function f in our space, you can find g in this subset within distance u. Now these two definitions are closely related, and this is left as a very simple exercise, right, to show that the covering number is bounded by the packing number, and the packing number is bounded by a covering number at u over 2. Okay, the first inequality will essentially see it in the proof of the next result, and the second inequality is, well, it's a simple exercise. Right, in our main result in this section, we'll be interested specifically in subsets of this cube in Rn, and the distance between vectors, well, it will be just rescaled Euclidean distance. So to match better with our calculation, we just rescale by square root of n. Okay, so in other words, it's just 1 over square root of n times the Euclidean distance between vectors f and g. And then we'll consider the process with these Rademacher random signs as above, which also is called Rademacher process. It's a function of indexed by f, given by this 1 over square root of n, the sum from 1 to n, these Rademacher random signs epsilon I times fi. So it's exactly what we have seen above, with the right scaling by square root of n. And then within this setting for a subset of a cube with this particular rescaled Euclidean distance and this Rademacher process, we will prove the following theorem, okay, which is called Kolmogorov's chaining lemma, which states the following, that for any u bigger than 0, we will be able to control this Rademacher process, which is a random variable, in a certain way uniformly, or for all f in our set f. So for all f in our set f, we'll have the following inequality, that the Rademacher process can be bounded by some constant, and we'll have some specific constants coming out from the proof. Integral from 0 to twice the distance between this vector f and 0 of the square root of the logarithm of the packing number. And here we view packing number as a function of epsilon, and then integrate this square root with respect to epsilon. Okay, plus there will be a second term, also the same constant, times the distance between 0 and f times square root of u, and this probability will be at least 1 minus e to the minus u. So in other words, you pick your u or you pick your guarantee, and then for all vectors f in this particular subset of the cube, you control this Rademacher process by the sum of two terms. Both of them depend on the distance of your vector from 0. And in this result, the first term here, this integral, is called Dudley's entropy integral. Okay, and the name comes from the fact that the logarithm of a covering number or logarithm of the packing number is called entropy or metric entropy. Okay, and in that integral we integrate square root of this entropy up to the twice the distance of f from 0. Okay, so the basic meaning of this result is that we are trying to control random variables Rf, this Rademacher process, simultaneously for all vectors in our set F. Okay, and this first term given by Dudley's entropy integral, it represents some sort of penalty that we have to pay for trying to get this simultaneous control. Of course, the bigger the set F is, the more difficult our task is, and so the size of the set or the complexity of the set here is measured through this metric entropy function. Okay, and we will see in the proof how it comes out very naturally. Okay, so to prove this result, okay, first of all, we will suppose that 0 belongs to our set F. Okay, and in some sense this is really without loss of generality, because if you add 0.0 to your set, the packing numbers will just increase by 1, and you can see that it will basically result just in bigger constants in the inequality that we are trying to prove. Okay, so from the beginning it will be convenient to assume that 0, it's already included in our set. Okay, then we are going to construct the following sequence of finite subsets of F. This sequence starts with the set, we'll call it F0, just consisting of a 0 vector. Okay, and then it will be increasing sequence of subsets inside F, okay, such that the following two conditions hold. So first of all, for all f and g in the set fj, they will be at the distance at least 2 to the minus j from each other. Okay, so in particular, the size of this set fj, the cardinality of this set fj, will be smaller than the cardinality of the optimal packing. Just by the definition of the optimal packing, you are trying to maximize the cardinality of the set at a distance 2 to the minus j. So this cardinality will be bounded by that packing function at 2 to the minus j. And the second property will be that this set fj will be 2 to the minus j covering. So in other words, for all f in our set, you can find a vector in fj such that the distance between them is bounded by 2 to the minus j. And to construct such sequence of sets, you can just proceed recursively as follows. Okay, so let's look at our set F, and okay, let's start at 0, and so at the level j equals to 0, well, the distance of all the functions from 0 is less than or equal than 1, okay, which is 2 to the minus 0. Then how we can construct the set with index 1? So we are looking now at the scale 2 to the minus 1. And so we simply are going to keep trying to find functions f at the distance at least 1/2 from what we have. So we try to take the next function, if possible, at the distance strictly bigger from the previous one. And so we keep doing this as long as we can find such functions. Now, once we cannot find any more such functions, that means that the second property is automatically satisfied. All the functions left will be within 1/2 from one of these. Right? And then we just continue something similar for all j. So you take j equals to 2, you're looking at the scale 2 to the minus 2, and then you keep finding functions, if possible, at the distance 2 to the minus 2 from the previous functions, and try to find these, okay, if you can. And then you continue this process, right, for a general scale 2 to the minus j. You keep finding functions at the distance strictly bigger than 2 to the minus j from the previous functions until you can no longer find them, and then the second property is automatically satisfied. Now, once we find this sequence of sets here for these dyadic scales 2 to the minus j, then we are going to define the projection from our set to these fj just by taking the closest. Okay, so we'll define this projection pj from f to fj simply by choosing the closest point within distance 2 to the minus j, so such that pj of f, right, is the closest in fj to our point f. Okay, and we break the tie arbitrarily. Okay, now in particular we know that the distance from f to pj of f is less than 2 to the minus j. The closest point must be within this distance. And then we can represent any function f in our set as the telescopic sum of the increments between these projections, okay, which we will call the sum of links. Okay, and the basic point here is that if you have some point given by this yellow dot here in your metric space or in your subset, okay, you start with 0 and then you find the closest point at the scale 1/2, and you look at the difference, the increment between these two vectors. Then you find the closest point at the next scale and you look at the difference of these two vectors. And then you find the closest point on the next scale and you get the difference between two vectors, and so on. So this can be viewed as the links in this chain, which approximates your point f, arbitrary point f, closer and closer with each step. Okay, so the size of these links is getting smaller and smaller. Okay, and this is the main idea of this Kolmogorov's chaining method, to consider this multi-scale dyadic approximation of all the vectors in your set, and then represent your function as the sum of links when you go from one level of approximation to the next. And as we will see in a second, of course, on the one hand, the number of links is getting bigger and bigger as your approximation gets better and better, because just the size of these sets is growing. But on the other hand, the size of the links is also getting smaller and smaller, and because of the Hövding's inequality, we will have an excellent control of the Rademacher process on the links, right? Because our Rademacher process is linear, is a linear function, so you can write it as a telescopic series of the Rademacher process applied to these links given by the difference of two consecutive approximations. And because the size of the link is getting small, we will have a very good control of this Rademacher process. Okay, now let us notice that if these two consecutive approximation sets are equal, then the projections will also be equal. So in particular, what we call the link between these two levels j-1 and j will be 0 for this function, or for any function. Okay, and to see that this is the case, well, you can just notice that otherwise, okay, by contradiction, if you suppose that for some function these two projections are not equal, then what does it imply? Well, first of all, because both of them belong to j-1 or fj-1, by definition, the distance between them should be at least 2 to the minus j-1. Okay, but on the other hand, because this was the closest point to f, and both are in fj, that means that the distance from projection pi j should be less than or equal than 2 to the minus j, but also the distance to the projection j-1 should be less than 2 minus j, right? Because it must be the closest point. But of course, this by triangle inequality, this contradicts that the distance between these two projections is bigger than twice 2 to the minus j. And so that's not possible. That means you have a unique closest point at level j, and at level j-1 it's the same thing. Okay, so in this case, we'll let the set of links between j-1 and j to be just 0, because the link that we consider above is 0. Now, in the case when these two sets are not equal, so fj is strictly bigger than fj, then by the triangle inequality as above, we can bound the distance between approximation at level j-1 and approximation at level j just by triangle inequality comparing the distance from these to f, right? We can bound it by 2 to the minus j-1 plus 2 to the minus j, which is 3 times 2 to the minus j, and just for convenience we'll write this as a power of 2. So in particular, we can define now the set of links between approximation j-1 and j to be all increments of the form f minus j, where f comes from fj, g comes from fj minus 1, and we know that the distance between them must be bounded by this quantity here as above. So no matter what the function f is, the link or the difference of the projection must belong to this set. Okay, and this would be true even if fj minus 1 and fj are equal, but we'll see why we considered this set separately and why we wanted to show that this set is actually 0. Well, now we are going to finally use Hovding's inequality, and we'll see why we had to symmetrize in the first step and introduce these Rademacher random variables. Okay, so if we take one element in this set of links, then by Hovding's inequality we can control the Rademacher process on this link, which is just 1 over square root of n. Okay, the sum epsilon I Li. The probability that it exceeds any positive constant t by Hovding's inequality is less than e to the minus t squared over 2 times the sum of squares of these coefficients in front of epsilon i's. So 1 over n, the sum over I from 1 to n, Li squared. Okay, but we know that this link in this set, okay, has this distance from 0 is bounded by this 2 to the minus j plus 2, and that's exactly this average of squares here. So we can bound this by e to the minus t squared divided by 2 times 2 to the minus 2j plus 2, because this here in the denominator is the distance squared. And this inequality, well, this was just by Hovding's inequality. Then we use the union bound. So we want to control all links simultaneously. So probability, and I'm going to go to the complement. So for all links in this that connect level j minus 1 to j, we control the Rademacher process on this link by t with probability at least 1 minus the sum over all these links, so that's the cardinality of the set of links, times the exponential above. Okay, so that's just by union bound and going to the complements. And then the number of links between level j minus 1 and j is just the cardinality of fj minus 1 times fj, which is bounded by the cardinality of fj squared, and so we get this lower bound. And so here we see this kind of competition between complexity and the size of the link, right? So the number of links here grows with j, but at the same time the size of the link, or the distance, Euclidean distance of the link from 0, is reflected here, that the length gets small. And in particular, because we chose this dyadic approximation, we can see that this exponential is actually a double exponential with j. Now, of course, the cardinality of the set of links can also grow fast, but in any case, here we have this kind of competition between the complexity of the class and the size of the links. And what we are going to do next is make a change of variable so that the quantity above is 1 minus 1 over this cardinality squared times e to the minus u. Okay, so in other words, the change of variables here is if you solve for t in terms of u, we take t to be square root of 2 to the minus 2j plus 5, 4 times the log of the cardinality of fj plus u. Okay, and then we take the square root of this. For simplicity, we will just bound the square root of the sum by the sum of the square roots. So this is bounded by 2 to the 7/2, 2 to the minus j, square root of the log of this cardinality. Okay, and then you see where the square root of the log of the packing number appears in this calculation. Okay, plus 2 to the 5 halves, 2 to the minus j square root of u. And we made this change of variables because we also want to control all these links for all levels j. So we want to actually take another union bound and write that the probability that for all j and for all links between level j minus 1 and j, the Rademacher process on the link is bounded by t, and t was now replaced by this quantity here, so I will not copy it here, right? But now by the union bound, you have to also sum over j. So this will be sum over j of the above bound, which was 1 over this cardinality squared e to the minus u. And here I can also put the indicator that fj minus 1 is not equal to fj, right? Because we discussed above that if fj minus 1 is equal to fj, then the link is actually equal to 0. So the set of links between those two levels is just 0, and there is nothing to control. So we only need to control this probability when the next approximation set is strictly bigger. And so this series includes the terms which increase at least by 1 at every step. So as a result, the cardinality here will be at least j plus 1 squared, because at level j equal to 0, we start with 1 point. Cardinality is 1. And in this form, the series in front of the exponential converges. In fact, in this case, this is a famous series, pi squared over 6, missing the first term. But for us, it only matters that it's some constant, and in this particular case, it happens to be smaller than 1, so this will be at least 1 minus e to the minus u. So we now obtain a set with the probability that we want. Probability is at least 1 minus e to the minus u, so that the Rademacher process of the link is controlled for all levels j. Okay, and now it just remains to deduce the bound on the Rademacher process at any given f given by this telescopic series from this information. So namely, if we recall that Rademacher process of f is just the sum over j of Rademacher process of these links, these increments belong to a set of links, and then we also want to take into account the distance of our function from 0. So let's suppose that the distance of f from 0 is between 2 to the minus k plus 1 and 2 to the minus k. So choose such k, okay, and then if your f is within distance 2 to the minus k from 0, then you can conclude right away that projections of f up to the level k minus 1 will be 0. So in other words, 0 will be the closest point up to the level k minus 1. Okay, and this is true because, okay, for j up to k minus 1, if you take any other function in fj which is not 0, then the distance from 0, just by definition, has to be at least 2 to the minus j, which is at least 2 to the minus k plus 1. Right? And here we have information that f is within distance 2 to the minus k. So 0 has to be the closest point up to that level. So in particular, in this telescopic series here, the sum will start at k. Until then, the links are 0. So the sum will be for j greater or equal than k. Okay, and then on the above event of high probability, we can control the Rademacher process of this link by, well, I just copy the bound above. It's 2 to the 7 over 2, 2 to the minus j, square root of the log of this cardinality of fj, plus 2 to the 5/2, 2 to the minus j times square root of u. Now in the first sum, first I'm going to multiply and divide by 2, so I'll write 2 to the 9/2, and then sum, I'll put minus j minus 1, minus j plus 1. Also, let's recall that the cardinality of the set fj was bounded by the packing number at epsilon equal to 2 to the minus j. So that's the first term. Well, the second term is just geometric series, so you can see that you get 2 to the 7/2, 2 to the minus k, square root of u. And for the second term, we chose 2 to the minus k to be smaller than twice the distance of f from 0. So this is bounded by 2 to the 9/2, the distance of f from 0, square root of u. And that's exactly the second term in the statement of this theorem. And for the first term, well, we see that this is just approximation of the integral, of the Dudley entropy integral. Indeed, if you graph this function, square root of the log of the packing number as a function of epsilon, right, by the definition, this function is decreasing with epsilon. Okay, so it will look something like this. And then in the sum above, we start with evaluating this function at 2 to the minus k, right, and then multiply it by half of this interval. So, right, you can go up to half of this interval, and the product is just the area of this rectangle. And all the other terms are just these rectangles where you evaluate and multiply by half of this interval, and so on. Right, so this sum, the series, is the area of all these rectangles under this function. And then we recall also that 2 to the minus k is again bounded by twice the distance of 0 from f. That's how this k was chosen. Okay, so as a result, the above series is bounded by 2 to the 9/2, integral from 0 to twice the distance of f from 0, square root of this entropy, and the second term is also 2 to the 9/2, distance of f from 0, square root of u. And if you go back and check, that's exactly the statement of the theorem, that probability that the Rademacher process can be controlled by this quantity for all f in our set f, probability of this is at least 1 minus e to the minus u. And that's what we proved. Okay, and everything until now was quite general, applies to any class of functions or any subset of this cube on Rn. So the only thing that is left is to consider the set of indicators that we started with in this particular case of empirical process, and to see how we can control this metric entropy for the set generated by those indicators. Okay, so let's recall that we started with this particular set generated by indicators of the following form for s minus t less than or equal than delta. In this case, this restriction by delta will not really matter to us, so we'll just increase and consider the set f tilde of all indicators of this form, s and t in 0, 1. And what we'll show right now is the following lemma, that the packing number of this set f tilde with respect to the distance d at epsilon is bounded by some constant over epsilon to the fourth. And we can even get an explicit constant here. Okay, and I recall that the distance between two vectors that we work with is just rescaled Euclidean distance. So to prove this, first of all, notice that by permutation we can assume that xi's are increasing, right? Because the distances above are not affected by permutation of the indices, so we can just permute x's from the beginning to assume that they form an increasing sequence. So in this case, once we permute the set that we are looking at, well, this is just indicators that xi's fall in between some numbers s and t. So it will be vectors of the form 0, so it will be some zeros until xi will be greater than s, then there will be ones until you cross t, and then there will be zeros after. So our set of vectors will be anything of this form, where we'll denote the starting index here by s and the last index by f. So where this starting point and final point or finish point is anything between 1 and n. All right, now we are going to simply discretize. So given epsilon, let's consider another set, let's call it f prime, of vectors of the same form, so with consecutive ones somewhere in the middle. Okay, but in this case, the starting point and the finish point of this sequence of ones will be not any index from 1 to n, but indices of the form proportional to epsilon. So it will be n epsilon rounded down to the integer 2, n epsilon, and so on, where the final index will be something of the form very close to 1 over epsilon n epsilon. And how many do we have here? So if you look in this discretization of the starting points and ending point proportional to n epsilon, basically you have 1 over epsilon possibilities. So the cardinality of this set f prime is bounded by, well, you have to be careful, so maybe it's not 1 over epsilon, slightly bigger than that, so I'll just bound that by 2 over epsilon, and then because you choose both starting and finishing point, the cardinality will be bounded by this squared. And finally, it remains to notice that any vector f in f tilde can be approximated by one of these discretized vectors within a small distance. So namely, if you take a vector f in f tilde, then you can pick a vector g in f prime, okay, by simply choosing the starting point and the ending point of the sequence of ones as close as possible. That means within n epsilon coordinates. And then the distance between these two will be bounded by, well, how many coordinates will actually be different. You might have at most n epsilon coordinates different at the beginning, and at most n epsilon coordinate at the end. So that's how many coordinates will be different here, and their difference is always 1 for these indicators. Then you take a square root, and so you can see this is actually bounded by square root of 2 epsilon. And of course what this means is that the covering number of our set f tilde, with distance d at square root of 2 epsilon is at most the cardinality of this set f prime, right? Because the points in f prime approximate all other points in the set we want within this distance. And we already said that the cardinality is bounded by 2 over epsilon squared. Okay, and to finish the proof, we just recall that the packing number at any given u is bounded by the covering number at u over 2, right? And just making the change of variables here, you get some constant over u to the 4th. Okay, and now it remains to plug in this estimate on the packing number into the previous result, into Kolmogorov's chaining bound. Namely, if we let dn to be the supremum over f in this set of indicators that we are interested in of the distance of the vectors f from 0, then the previous lemma, well, we had a control individually for each function of the Rademacher process. But here I'm going to take supremum over all f in our class of the Rademacher process. So as a result, we'll also get a supremum in the upper bound. Namely, in the integral from 0 to 2 times the distance will be replaced by the supremum of the distance. And then the square root of the log of the packing number now will be something of the form square root of the log k over epsilon by this previous lemma. And we have some constant in front. And in the second term, also we had some absolute constant times the distance from 0, but here I'm taking supremum, so that's replaced by the supremum dn. Okay, and then square root of u, I will replace it by t, so this probability is bigger than e to the minus t squared. So we get this by plugging the estimate on the packing number into the Kolmogorov's chaining lemma. And the last step, it's one-line calculation, which I'm going to omit. It's an exercise, or you can just check in the notes that if the probability that the random variable is bigger than a plus bt is less than some constant times e to the minus t squared, then you can estimate the expectation of x, or you can bound the expectation of x by some constant times a plus b. Again, using this inequality with this previous probability, where of course this first integral is a and this constant times dn is b, we get that expectation of the supremum of the Rademacher process for our class of indicators is bounded by some constant times this first integral plus dn, where, if you recall, up to this point all x's were fixed, so the only randomness was in the Rademacher random variables. So to be more precise, the expectation here is in the Rademacher random variables epsilon 1, epsilon n. Okay, and that's the inequality that we used to finish the proof of the convergence of empirical processes to Brownian motion in the first part. So that finishes this section.